Hello, everyone, and welcome to this episode. Today, we are beginning our magical journey into the land of acids, bases, and buffers. Or, if you're taking AP Chem, it's Unit 8. And so today, we have to get some background ideas about acids and bases out of the way, including some vocabulary. So you'll see some terms on the next few slides. And if at any point you want to stop the video and write them down, you are always welcome to do that. All right, so first, you may have already been exposed to the definitions of acids and bases. There are actually three of them put forth by Bronsted and Lowry, Arrhenius, and Gilbert Lewis. We'll get to Gilbert. We saw Gilbert in the last unit when we were talking about coordination compounds. But we're mainly going to be focusing on the Bronsted-Lowry definition of acids and bases, which that is that an acid in a reaction is a proton donor and a base is a proton acceptor. And you might be wondering, why am I calling H plus a proton? Isn't that hydrogen? Well, yes, that's true, but hydrogen really only has one proton. And if you take away its electron to make a positively charged ion, you end up with just the proton. So we use those two terms interchangeably. Okay, so an acid is a proton donor, a base is a proton acceptor, and lots of really cool chemistry happens because of those exchange of the protons. Now, it's good to differentiate between a strong acid and a weak acid. And a strong acid is one that donates 100% of its protons. It's just really, really good at being an acid. And so it donates all of its protons, 100%, and you should know that there are six of them. I've listed them here off to the side. You should kind of get to know those, and whenever you see them, it should, get your spidey sense tingling that those are strong acids and we need to dissociate them 100%. So take a moment and note them. Here's some diagrams showing HCl dissociating, and when it dumps its proton, those protons go onto a water molecule to make a hydronium ion. And that hydronium ion is present in solution. So there's really, sometimes we actually write that there's an H plus in solution. It's really actually an H3O plus because it pops onto a water molecule. And I'm just going to write this for the sake of those of you who would like it. That's hydronium ion right there. Okay. And nitric acid does the same thing. It's important to note that in these solutions, there really is no HCl and no HNO3 to speak of. It's basically all been converted over here. All right, so if strong acids are the ones that donate 100%, what is up with the weak acids? The weak acids they're acids, they'll give away some protons, but they don't do it 100% of the time. In fact, a lot of the times, most of the acid molecules still have their protons. They prefer to have those protons, but they'll set up an equilibrium where they donate some protons to the water, and that begins to increase in concentration. But as that does, the odds of this connecting with this again and reattracting its proton increases, and so eventually you get an equilibrium out of that. This is acetic acid. There are lots and lots of weak acids because there's only 6 strong acids. All the rest of them are weak. Okay, so let's revise our definitions slightly. Strong acid is one where the acid dissociates 100%. Or you could also say its equilibrium lies far to the right, meaning it has a really, really big equilibrium constant, so much so that it's very difficult to measure. Okay, a weak acid is one where the acid dissociates less than 100%. It sets up an equilibrium, and the equilibrium lies far to the left. There's actually not a lot of protons being formed from most of the weak acids. And as you might expect, since they set up equilibria, we can actually write an equilibrium constant expression. And we call this the Ka, the acid dissociation constant. And for a generic acid like this one, HA, A is just generic anion, plus water makes H3O plus and the anion. These are our two products, and we have H3O plus and A minus over HA. And the water is not included because water is the pure liquid that all this stuff is swimming around in. And because it's pure liquid, it makes it heterogeneous, and we don't include that. So you'll see this a lot. This appears on, for example, the AP chemistry formula sheet that you might end up using, but that's the generic version of it. I'm including here a table of some acids. You're probably going to get one in your class as well. You can find them all over the internet if you want to. And this is just a portion of one of the tables that I have. And I wanted to show it because up here we have 4 of the strong acids listed there, and their Ka values are very large. All right. And then as you get down into the weaker acids, they get to be like 10 to the minus 2, 10 to the minus 3, 10 to the minus 4. And they continue to get smaller and smaller from there. But if you don't have one of these already, you should search the internet or ask your teacher for a chart like that. Because, of course, we don't have to memorize all of those. All right. It's also important to note that some acids are diprotic, meaning they can donate 2 protons. Sulfuric acid is it's the only strong acid that can give away a proton, which it does 100%. Notice the single arrow there. But it produces another molecule, an ion, HSO4 minus, which has a proton that it can donate as well. So it'll donate the first one 100% and this one less than 100%. But it has 2 protons that it can donate. And it goes on from there. Some acids are triprotic, like citric acid has 3 protons, and so forth. All right, let's talk about bases for a moment. Weak bases accept protons. That's what Bronsted-Lowry definition says. And some are strong bases. They'll accept all the protons they can. And there's a short list of strong bases. Those are the alkali metal hydroxides, sodium hydroxide, lithium hydroxide, potassium hydroxide, and even including barium hydroxide in some charts, because that's a fairly strong base. All the other bases are weak, and they accept protons, but not 100% of the time. These also have equilibrium constants, which are denoted Kb. Okay. All right, let's talk about conjugate acids and bases. And conjugate acids and bases are related species in a reaction where the acid donates a proton and becomes its conjugate base. All right, the acid in the forward reaction becomes the conjugate base for the reverse reaction. So the conjugates are the acid and base for the reverse reaction. And since it would have to reaccept the proton to become this again, it would be a base. And in the reverse reaction, the thing that's donating the hydrogen back would be the hydronium ion. So that is the acid, and it's the conjugate acid of water. So I'll say it a different way. The conjugate base is the acid after it donates its hydrogen. And the conjugate acid is the base after it has accepted the hydrogen. All right, try to figure out a way to keep track of those. And conjugate acids and bases have different strengths because of the way they start. So, for example, hydrochloric acid is one of the strong acids. It'll donate 100% of the time, which means that its conjugate base, chloride ion, is very, very weak. It's not really able to pick up those hydrogens and go back to being HCl again, because even if it did, it's just going to dump back over and be the chloride ion again. So it's a very weak conjugate base. So the stronger the acid, the weaker its conjugate base. The weaker the acid, the stronger its conjugate base, and vice versa. Okay? And let's take a look at a weak acid and its conjugate base. Here's our acetic acid and its conjugate. So acetic acid only dissociates a few percent of the time, maybe around 5, give or take, depending on the molarity, and it becomes this. But this is actually a fairly strong conjugate base. It would rather have its hydrogen back. So if it gets a chance, it bumps into one of these and it'll get its hydrogen back and go back to being acetic acid. So it's all about proton donating and accepting. Okay, quick question. Fun fact. What is the world's most common acid? And you might think of something like hydrochloric or nitric or something that you've heard of. The most common acid in the world, in the universe, is water. And this is where things get really fun and interesting. Water itself is an acid. And if that scares you for a moment, you're like, wait a minute, what? It's an acid? Really? Yes, it is, because it has hydrogens that it can donate, and it does donate them. It is also the world's most common base, which, again, what? Yeah, it's an acid and a base. It's one of those things we call amphoteric. And it's really common and all that stuff. So get this. Under any circumstances, under normal conditions, you can imagine you have water molecules, and they're bumping into each other and so on. Water molecules can act like acids, they can act like bases, and they do both at the same time. So imagine 2 water molecules bumping into each other. One of them donates a hydrogen to the other one to become a hydronium and a hydroxide ion. And This happens to a small extent in any water-based solution, even pure distilled water. And it actually sets up an equilibrium with each other with an equilibrium constant, which is very special. We call it Kw, which is the water dissociation constant. And that's going to be equal to the H plus concentration and the OH concentration over these, which are the liquid, so we don't include them. But at normal conditions, that constant has a value of 1 times 10 to the minus 14th. And that's kind of what governs everything that happens in water. Now, I'm assuming you're a curious type person, and you've probably learned a little bit about the pH scale back in maybe elementary school or middle school or something like that. And you probably know that the pH scale goes from 0 to 14. And I don't know about you, but sometimes that kept me up at night, wondering why 14? Why does the pH scale go from 0 to 14 and not like 0 to 10 or 20 or 100, something nice and easy, and so on? And we can start to get a clue about that because of the magnitude of the equilibrium constant, which is 10 to the minus 14. All right, and you might have also wondered, why does water have a pH of 7? Why not 10 out of 20 or 50 out of 100? Well, it turns out that for any solution, hydrogen ion plus the OH ion concentration is equal to that constant. It governs everything that happens in aqueous solution. And so if the amount of acid protons is equal to the base hydroxide ions, they're going to both be equal to the square root of that number, which is 1 times 10 to the minus 7th. Okay? And in any aqueous solution, sometimes there's more hydrogens than hydroxides. If the hydrogens go up, the hydroxides go down, and vice versa. But they will always multiply together to get 1 times 10 to the minus 14th. So I've got this chart over here where in a neutral solution, 10 to the minus 7th, you can get all the way down to 10 to the minus 14th moles per liter and a little bit beyond, or all the way up to 1 mole per liter and a little bit beyond that. But the OH concentration is changing in response to that in the opposite way. So again, why does water have a pH of 7? Well, 7 is the exponent that it has when it's a neutral solution, 10 to the minus 7. And so we actually have a couple of definitions for us. The pH is actually defined as the negative log, the negative is there to change the sign, of the hydrogen ion concentration. Okay, and in pure water, that's 10 to the minus 7th. So the log of 10 to the minus 7th is minus 7, but a negative of a minus 7 is 7. There's also a pOH, which responds opposite to the pH. So if the pH is 14, the pOH is 0. If the pH is 0, the pOH is 14. And that's defined as the negative log of the OH concentration. In any case, the pH plus the pOH is going to add up to 14. Okay, that's one of our tools that we use. It's an equation, and you'll find it on your equation sheet probably. And this one we already started with, H plus OH makes 1 times 10 to the minus 14. A quick little note before we do some problems. We'll have a couple pause the video moments. That equilibrium constant is temperature dependent, as all equilibrium constants are. And as you look at this temperature, at 25 degrees, you're talking 1 times 10 to the minus 14th. At 10 degrees, it's lower. At 50 degrees, it's higher, which indicates that autoionization of water is endothermic. And we learned that in Unit 7. All right, let's try a couple of quick things. So the pH of a sample of blood is 7.41. Let's calculate the pH, the H plus, the OH minus, and the pOH for this solution. Okay, so I've been given the pH, and I know that the pH equals the negative log of the H plus concentration. And I can put the pH in there. But I want to talk about how you would rearrange this and do the math. To rearrange this equation to solve for the H plus concentration, you actually end up raising 10 to the negative of the pH value. Okay, that's just a rearrangement, and that's something that you will likely see on an equation sheet as well. So we're going to make it go 10 to the negative 7.41. And if I do that properly, I'm going to get the H plus concentration to be 3.9 times 10 to the minus 8. And that is in moles per liter. Okay. And a quick note about pH values. pH values should always have 2 decimal places, regardless of the sig digs that are happening in other places in your calculations. By convention, pH values always have 2 decimal places, so don't forget to put those. Even if it's like 7.00, make sure you put those. All right, the next one, I want to find the OH concentration. And I've been told that H plus times OH minus equals 1.0 times 10 to the minus 14. Okay, so I know what this is, 3.9 times 10 to the minus 8th times the OH concentration will equal 1 times 10 to the minus 14th. And the OH concentration here becomes 2.57 times 10 to the minus 7th moles per liter. So I'm going to highlight that, put little hearts next to my stuff. And then I want to get the pOH. And the pOH here is the negative log of the OH concentration, which I just found. And that's going to be 2.57 times 10 to the minus 7th. And the pOH here is going to be 6.59. And there's a second way I could have done the pOH. I could have taken 14 minus the 7.41 because these two should add up to 14. And you're welcome to do that as well. All right, let's take a moment and do a pause the video moment. Our job for today is to get used to doing and using these types of equations. So take a moment. The pH of a glass of lemonade is 4.49. See if you can calculate the H plus, the OH, and the pOH for this solution. And if you were able to do that and come up with these numbers, then congratulations. We're well on our way to mastering these equations. I got an H plus concentration of 3.23 times 10 to the minus 5th moles per liter. That should have a moles per liter unit on it. pH values have no units, so don't put them on there. pOH is 9.51, which is 14 minus that number. I use that for this one. And then the OH concentration is 10 to the negative pOH, which is 3.09 times 10 to the minus 10th. And just for fun, we could do one more example. We'll do a pause the video moment for this in case you need more practice. The pOH of my morning coffee is 9.34. Fun fact, I like my coffee black, no cream, no sugar, no creamer, and anything like that. But if my pOH is 9.34, take a moment, pause the video, and calculate the OH, the H plus, and the pH. All right, and here are some answers. Check your work and see if you got those. And if you did, great. Congratulations. You're mastering these little equation tools that we have to deal with H plus, OH minus, and pH and pOH in solution. Okay, let's move on with a couple of final thoughts, a couple of random things. Let's do this one first. So here's a table of conjugate acid-base pairs. And there's more than this. This is just kind of a bridge table. So if the acid, for example, is hydrochloric, its conjugate base is chlorine, chloride ion. Nitric, its conjugate base is nitric or nitrate ion. Notice these are single arrows, not double arrows, because those are strong acids. They don't go to equilibrium, they just go all the way. The rest of these are weak acids, so you'll see their acid formulas and their conjugate base formulas. All right. Now, because these are weak, they set up equilibria, and so they have equilibrium constants. These have Ka values that represent how far they'll dissociate, and these would have Kb values, which would represent how far they go to the right and accept their protons. And a little fun fact, another tool that we have about water-based solutions is that we know what Kw is. That's the acid dissociation constant for water, 1 times 10 to the minus 14th. And if you know the Ka for your acid, for example, the Ka times the Kb equals the Kw in all situations. So if you know the Ka, you can solve for your Kb for its conjugate. Or if you know Kb for the base, you can solve for Ka for its conjugate. And we'll use that tool as we go through this unit quite a lot. In general, acids are strong. The strong acids have weak conjugate bases. Weak acids have strong conjugate bases. So again, another representation of that. So overall, a couple of final thoughts. As acid strength increases, the Ka of the acid increases, the Kb of its conjugate decreases, and H plus increase and the pH decreases because pH is the negative log of the H plus concentration. As base strength increases, the Kb and the OH increase. Kb gets bigger and the pH also increases because it's the negative log of the or hydrogen ion concentration. And you can see a little graphic on that. And finally, pH ranges for weak acids and bases. So strong acids, if you have any reasonable quantity of the strong acid in your solution, you're going to have a low pH, somewhere between 0 and 2 maybe, but something pretty extreme. Same with strong bases. If you get sodium hydroxide in solution to any measurable degree, you're looking at 12 to 14 on the pH scale. But the weak ones, which set up equilibria, generally make pHs between 2 and around 7, or 12 and around 7 for those weak bases. You're above and below 7, but you're kind of near the middle. For practical purposes, yes, 7 is neutral, but anything between 6 and 8 is often considered neutral too, because they're pretty close to being neutral, and you're not going to melt your skin off by dunking your finger in there. But those are some ranges. So if you see those pH ranges, you're probably looking at a weak acid or a weak base. All right. So that was some basic information about some acids and bases and the stuff that happens in water and those formulas that we have to be able to use. I hope you found it helpful. You may find it helpful to rewatch this video at some point just to kind of get those terms in again. But in the meantime, if you have any questions, comments, or concerns, you can send them to me in the comments or directly. And in the meantime, happy solving and have a great day.